Okay, thank you. Yeah, I'm Ignacio. I'm a postdoc at Amsterdam. Is this key? Thank you. And I would also like to thank the organizers for the opportunity to talk here. So I'm going to tell you about something that should be out very, very soon. And it's an application of quantum field theory to the problem of the stability of stars. So let me start with a very simple observation that probably everyone in this room would agree with, which is related to the Planck scale. So if you start with classical general relativity with matter, you realize that the stress tensor, its components, are proportional to the curvature. The coefficient, the factor of proportionality, is G Newton. Now, if you introduce now quantum corrections to this matter or other fields, what you generically find, this is very hard computations to do, but after you renormalize, what you typically find is that the expectation value of the renormalized stress tensor scales as the square of the curvature, and in that case, the proportionality factor is h bar. So then when you ask the question, well, when do these components, so the classical components, become of the same order as the quantum components, you immediately realize, because of what I just said, that this only happens when the radius of curvature is of the order of the Planck scale. Or in other words, if the density is close to the Planck density. So therefore, we can neglect the quantum effects due to the curvature of spacetime if we're below the Planck scale. Now this simplicity of this argument does not prevent it from being completely wrong. And I'm going to explain you why. And it's very easy to see it. So I'm going to derive this using the trace anomaly. So what does this mean? If you do quantum field, if you study quantum fields coupled to gauge fields, in this particular case, general relativity, generically anomalies appear. In this case, we're doing quantum field theory in curved spacetime. What does this mean? So the total stress tensor contains two contributions. One is has this index m here, which refers to a possible mass term. So this contains the contributions that break conformal symmetry already at the classical level and of course at the quantum level as well. And they do not depend explicitly on the metric. This is something that you're supposed to solve. You put it into the Einstein equation and you solve the equation. On the other hand, there's another contribution, which in this case is the anomaly. And it is explicitly dependent on the curvatures. It grows quadratically with the curvatures, as I said before. Now, in 3+1 dimensions, the Weyl conformal or trace anomaly is the statement that this last contribution, the anomalous contribution, is completely fixed, and it depends. It's given by this formula, where the first term is the square of the Weyl tensor, and the second term, E, is the Euler density or the Chern-Gauss-Bonnet density that appears in the Chern-Gauss-Bonnet theorem. So it's the thing that if you integrate it over the manifold gives you the Euler characteristic. It's a topological term. Now there are two coefficients associated. These are two central charges. They're very well understood. I'm not going to focus on them. They're not going to be important. The thing that will be important is that their signs are completely fixed. So given a theory, these coefficients depend on the Lagrangian. If you give me a Lagrangian, we know what these coefficients are. Okay, so that's the conformal anomaly. So I'm going to make a set of assumptions and then show you what the result is of a very trivial calculation. So I'm going to assume that if we're much below the Planck density, so still the Planck scale is very far away, first of all, I assume that the semi-classical approximation is the description of the system. Okay, and that means that the metric is still classical, and the stress tensor has these two components, as I said before. Assumption number two is that is something about the behavior of the equation of state of the matter at high energies. And the assumption is that matter at very high energies, still below the Planck scale, looks conformal at leading order. And I expect this to be true of essentially all theories. So what does this mean in practice? It means that if you take the trace of the matter component, these two terms, for an exactly conformal field theory, these are going to vanish if you put the mass to 0. But the statement is that this thing scales. This doesn't need to vanish exactly because we're approaching a conformal fixed point. But the point is that this has to scale with some power that is smaller than 1. So this quantity over here scales with the density, but in a way that is slower than linear scaling. Finally, there's this m here, which is whenever you just write the equation of state of a system, there's going to be some mass scale that appears. I'm just calling that m, and I'm going to tell you what it is in an example. The last assumption is that the individual components, if you compare component by component of the anomalous stress tensor, they are all subleading with respect to the matter, the fluid contributions. So what do we get out of this? So now consider taking the trace of the semi-classical Einstein equations. In 4 dimensions, the left-hand side just gives the Ricci scalar. And on the other hand side, we're going to have the sum of these 2 traces. But we already know what these 2 traces are. That's what I told you in the last 2 slides, right? So the matter contribution is exactly what I just showed. So it scales slower than a linear power. That's because we're approaching, the theory is looking more and more conformal. And on the other hand, we have the anomalous contribution. Now, if you simply use the assumptions that I just showed you, it's an absolutely trivial exercise to realize that if you take now the trace of the Einstein equations, you see on the right-hand side, you have the contribution of the matter, of the fluid, plus the contribution of the anomaly. I told you this scales quadratically with the densities as usual. So now when I ask the question, not of when do component by component these 2 objects become of the same order, but rather when do the traces of these objects become the same order, the answer is not the Planck scale, but rather this thing over here. So what I'm asking is when does this contribution, the anomalous contribution, the quantum contribution, become large enough such that it has an impact on the Ricci scalar? So I essentially put this to 0. This is this value over here. So the Ricci scalar, what does this thing do? At low densities, this thing scales as the linear term. That's standard, let's say, classical physics. But at some point, the anomaly kicks in, the Ricci scalar, and because the sign is fixed, that's completely fixed by the trace anomaly in 4 dimensions. You cannot choose the sign. You cannot choose the coefficients. This means that eventually the Ricci scalar reaches a maximum, goes to 0, and changes sign. And the point where it changes sign is given by this density over here that I just got from this equation. And what you'll see is that the critical density where the anomaly becomes macroscopic is not the Planck scale, but it's the Planck scale multiplied by this ratio over here. And it's the ratio of the mass scale that appeared in the equation of state divided by the Planck mass to a certain power that depends on alpha. That was the number that appeared in the equation of state. So let me consider the most important, or I think the most interesting example if I'm doing astrophysics. If I just take the Fermi gas at 0 temperature, I'm just telling you what the answer is. Alpha, that example corresponds to alpha equals 1/2. The mass appearing in the equation of state is the mass of the electron. If you evaluate this density, it's 30 orders of magnitude below the Planck scale. So why is this relevant? A very simple application is to consider the problem of degenerates or compact stars. So if you open the Bible on compact objects, there are 2 big results in this field. One is coming from the 1930s. That's the theory of degenerate stars, which only uses the Pauli exclusion principle. The anomaly was not even known by this time. So of course, they cannot take it into account. The second important result is not related to the stability as is the first, but rather to the existence of static solutions, and that's due to Buchthal in 1959. So what does Buchthal theorem tell us? Well, it tells us that if we take a static spherically symmetric perfect fluid, and you want to solve the Einstein's equations, without solving them and without assuming anything about the equation of state, you can only assuming that the density is positive, that it is non-decreasing outwards, and that the Einstein equations hold, you can show that there's a bound on the ratio. If you have a sphere of mass m and radius r, there's a bound on the compactness. And that lies a finite distance away from the black hole, from the Schwarzschild radius. So this is happening much before. And what's happening in the Buchthal limit is that the central redshift is going to infinity. So the metric is degenerating at the center. And that's the limit that I'm interested in. So finally, the question I wanted to understand is how do you assess the stability of an object, say, close to the Buchtel limit? So a very compact star. Now taking into account what I just told you about the anomaly. So to do that, a very simple thing you can do is to just study scalar perturbations at the linearized level. You can, as usual, rewrite this thing as a Schrodinger equation by changing coordinates. And the point is what this effective potential that appears in the Schrodinger equation is. So what happens is the following. If you, say, consider the L equals 0 sector to make it easy, if you neglect the anomaly, or in other words, at densities below this critical density where the anomaly becomes important, this potential over here, I'm just telling you the result, this potential over here, its minimum is negative. That simply comes out of the wave equation. Okay, this is not obvious from this calculation, but that's just what you get. The fact that the minimum of this potential is negative implies that it hosts bound states that are unstable because omega squared is negative. So these are exponentially growing modes. This means that the star is unstable. Now what happens when the density at the center of the star reaches this critical density when the anomaly becomes important? The Ricci scalar changes sign, and the Ricci scalar is what controls the location of the minimum. So at that point, the potential changes sign, the bound states disappear, and this object regains stability under these perturbations. So in conclusion, we saw that the effects of the trace anomaly become macroscopic not at the Planck scale, but much before that. How much before? Well, it depends on two parameters that appear in the equation of state. For an electron, say, this is 30 orders of magnitude before the Planck scale. And if you study scalar perturbations of stars close to the Buchtel limit where this effect is important, then you realize that objects that you would have thought that are unstable under these kind of perturbations actually become stable because of the effect that I just described. So as an outlook, I only considered spin 0 perturbations, but of course the interesting thing is to look at, say, spinor, or spin 1/2, or spin 2 gravitational perturbations, and to understand how this all relate to the dynamical problem of gravitational collapse. Thank you.
Thank you, Ignacio, for the interesting talk. I will run only on the right side. If you hand the microphone to the left, I'm happy. So 1, 2, 3 questions.
I found that rather convincing, but I have a simple question. What is the quantitative size? If I look for a neutron star, for example, or things like that, how much is the change that you get in addition, that you gain, in order to have something stable instead of unstable? If it's only a change in mass of let's say, a few per mil or something like that.
Yeah,
it's theoretically interesting, but in practice it does not. So just a number on
it depends
how big is the effect?
Yeah. Well, I think that's the wrong, or it's not exactly the correct question, but maybe let me try to answer it in a slightly different way. Okay, sorry. So let me consider this case, for example. If I take a star made of degenerate electrons, say, this effect, well, the mass of the neutron is basically the same as the mass of the electron for these effects, so it doesn't matter. So you could consider a neutron star, for example. Now, the density of a neutron star is something like 40 orders of magnitude below this number. So this physics has nothing to do with the Chandrasekhar and Tolman-Oppenheimer-Volkoff limits. This is a physics that appears at a widely higher scale. The effect that I was talking about today doesn't correct in any way the results from the 1930s. This is something that appears at an incredibly higher, so this is 30 orders of magnitude below the Planck scale.
Yes.
exactly.
like that. It's not so much.
Right. But this means, yeah, but this means that this physics this can in no way be considered a correction to the theory of degenerate stars. Yeah.
What I wanted to get out.
Yeah, yeah.
It's an effect that is, once you reach really linear scales of 10 to 12 GeV or something like that, then it sets in 7 orders of magnitude.
Yeah.
I'm just, translating density, which is in
I agree.
So,
Yeah.
I look at the typical energy scale where it happens. So that's something like 10 to 11, 10 to 12 GeV. It's not, TeV or whatsoever.
No, I agree. I totally agree. Yes.
Okay, next question.
I actually have two questions. So one is very short on your three assumptions.
Mhm.
You made an assumption in the equation of state, right?
Yes.
Do you actually need conformal symmetry, or do you
No.
scale invariance enough?
I don't know. I'm not sure.
I would guess that scale invariance. Exactly.
Right.
It's just compare the onset of masses due to particle.
Yeah. No, that's correct.
Okay.
It's scale symmetry at leading order. Of course, it's broken at subleading orders. Yeah.
And the other is, if I would want to capture that in some numerical simulation of classical dynamics, I would need to add a term that represents the T mu nu of the anomaly, right? Have you considered what you would have to do?
So I didn't understand the question.
Well, if you just write down the Einstein equations and you would want to see that effect, you're not going to find it because you haven't added the trace, the anomaly, right? So you have to add a suitable term.
No, but you have to add the anomaly.
So what exactly does that term look like? Can you?
Oh, this one you mean?
Yes.
It's not known in general. So people have been working on this for decades to try to determine the components of this thing. But the problem is that the components are plagued by renormalization scheme ambiguities. So it's very hard to tell what the components are. But in the 70s, what people learned is that what is renormalization scheme independent is the trace of this object. So practically, I would say the only case where in higher dimensions, in 2 dimensions more is known, of course, but in 4 dimensions, the only case that I know where the components of this object are known, so if you wanted to solve the full Einstein equations, is in the case where you have a conformally coupled theory and the background is conformally flat. In that case, you know exactly, there's an explicit formula for this in terms of the Riemann tensor and so on. Yeah.
So last question over here, please.
I think I must be misunderstanding something fundamental. Can you help me understand in your equation for the breaking of the conformal scaling of the
This one.
classical piece of the stress tensor, why it is that it doesn't... Did you turn off the mic? I must be misunderstanding something very simple. Can you help me understand in that equation why it is that this matter equation of state doesn't involve something like the number of particles of the thing, or the what is the parameter rho, for example?
It's the energy density.
Energy density.
Yeah.
Okay, so if I were going to make an estimate of that, for a degenerate electron star, I would,
Right.
For a white dwarf
Yeah,
star.
so in that case, let's say P would be the Fermi pressure,
Right.
and rho is, the other component in the stress tensor.
What would alpha be in that case?
Oh, 1/2, yeah. In that particular case, alpha is 1/2, and the m appearing in the equation, this m is the mass of the fermion. If you do quantum statistical mechanics, you take the relativistic limit. This is you can find this in the textbooks. This is textbook stuff. For that case, alpha is equal to 1/2, m is the mass of the fermion, and then if you just do quantum statistical mechanics, you take the ultra-relativistic limit, this is what you get at leading order.
Okay, thank you.
Okay, so we run out of time. Please postpone further questions to the coffee break and
Thank you.
to the speaker, please.